Two key things I was taught 15 years ago when I became a teacher. Two key ingredients, and that is flexibility and a sense of humor. And if you have those two things, you can make it in this career. And I've been very grateful for that advice. I think that when you're teaching about any controversial topic, there are a couple of things that you should know. But most important is you have to know yourself, and you should know your own bias. So just to be very clear, my bias comes from the fact that I'm a geologist. My perspective is that the Earth has been around for a very, very long time, and the only thing that is constant on this planet is change. The Earth will go on without us, and life will continue to exist unless we explode every nuclear weapon on the planet. But that life will continue. It just won't be the way we sort of think about it. So my interest in understanding climate change and finding solutions comes down to one very simple fact, that I'm a very selfish person. I would like a planet for my children to live on, and so this is my bias. This is where I'm coming from. I would like to have a place where my kids can go to the mountains and see what I've grown up seeing. And so it's an important thing to recognize kind of where you're coming from when you're getting started. And so after working with a lot of different people on designing curriculum and developing lesson plans, I've worked with people who've been very hesitant to teach the concepts of global warming, per se, or even climate change. And so I've kind of had to reframe it to keep them in their safe zone, kind of like this little guy. So I encourage them to at least talk about what is climate. How does climate work? What are the factors that control climate? Because I teach an earth science class, making sure that people talk about the history of not only the rocks on our planet, but also life and the atmosphere and the oceans. Integrating all of that into it develops an awareness amongst our students. So the idea that the past is the key to the present, the laws of thermodynamics are laws, they've existed since the dawn of time, and they are what controls so much of everything, and conservation of energy and mass. And finally, for those people who do teach environmental science or biology, the safe zone does exist within the topics of ecology, when you're learning about biomes and limiting factors, or the evolution of ecosystems, much less the evolution of a species. So these are all places that I refer to as the safe zone when talking about climate change. So I actually have worked with one particular person for 8 years. And when we first started talking about teaching climate change, she's like, don't want to do that, it's scary. Don't want to have any arguments with parents. Our parent population is already, has a fleet of helicopters. And they're constantly in our building, and they have no problem just interrupting you in the middle of class. And so that's a huge challenge for us. In some ways it's a blessing, but it's a challenge. And then after staying in the safe zone for a while, she decided that she was kind of waking up to this idea. She didn't quite look this bad, but she was realizing that she'd slept through a few things. For me, my awareness really was raised in the early 1990s. And it evoked a very personal and emotional response. I refer to it as my phase of fear and loathing on planet Earth. As a geologist and understanding extinctions, I was like, oh my gosh, are we going to be the one and only species that we know of that's actually causing the extinction of many, many, many other species? And do we have that right? And so I did what I was taught to do, and I started reading, and I read a lot. I took classes, and I started digging into data around ice and sediment and tree cores. My senior thesis as in my bachelor's program was collecting tree cores and understanding how landscapes change over time. So I already knew a little bit about dendrochronology, and so I was able to kind of learn from that. I learned about the Keeling curve, which is the CO2 Mauna Loa data. And so I started educating myself. And so when people ask me, well, where did you learn all this? I learned it by reading. And I didn't take a lot of really formal climate change classes, but I took classes in understanding data and getting data and trying to find out these things on my own. And that kind of brought me to what I refer to as a developmental stage. And these are sort of my early attempts at teaching climate change, and many of these were pretty much on my own. I would start with things like the Antarctic ice core. There are some really fun things you can do with tree cores and tree cookies. So this is what I refer to as a tree cookie. And getting kids, we had, when in 2002, when I first moved to Colorado, we'd just come through this horrific drought. And so when we bought our house, 40 trees on our property were dead. So we cut them all down to reduce the fire hazard like they told us to, and then I made my husband cut 2-inch chunks of slabs from all of them, and I was able to learn a lot. So from one 2-acre lot, what can we learn about the climate there over the last couple hundred years? I think we had data back to 250 years. And starting to show kids pictures of things like the glaciers around the world. And by the way, the U.S. Geological Survey has a website, and I will try to find it and I will get it up for you guys on the wiki, where they have put together these glacial pair pictures. So if you're interested in using these in your classes, they're very powerful, and the kids really tune into these. So focusing in initially on climate basics, and then getting into the history of climate through the data that exists. And remember, everything that we see right now, all the data is history of climate. It's not on the future, it's not on predictions, it's just the history. And that's that's very solid data. And we have so many different lines of data that I'm surprised we're not calling it at this stage a theory. Because if you think about the theory of evolution or the theory of plate tectonics, it's not one set of data, it's not 2 sets of data, it's literally thousands of sets of data that go together to encourage people to start thinking about something coherently. And I think that's a really important thing to teach our students. When we're talking about the nature of science, a theory is lots and lots and lots of lines of evidence, all pointing in the same direction. And that's the way the climate change is getting to at this point. And then finally, at this point of the game, when I was teaching just 2 years ago, I was trying to give this balanced education approach, which I can tell you can cause a lot of problems, okay? I was showing, one day I showed Inconvenient Truth, and the next day I showed The Greening of Planet Earth, which is a really awful video that's produced by the Western Petroleum Institute. And it tells you how wonderful carbon dioxide is and how all the plants are going to grow better. It's just, when you start digging into it, and then you start realizing that all the scientists they're talking to who funds their research, you get a really good sense of where this video is coming from. I was also doing student projects where they could go out and do research. And this was all from this sort of perspective of I have to teach both sides of the story. Well, surprise, but this is kind of what I got. In 2008, in the spring of 2008, I was called into the office, and I had a set of 6 parents who wanted me fired, and because I was proselytizing for the case of science. And I'm like, well, you can't really do that. Science isn't a belief system. It is what it is. And so I had to really start to dig in and kind of understand, where did I go wrong in this process? What mistakes have I made, and what can I fix in the future, and how can I not ever have to go through this again? The things that I didn't do very well is, while I know my students really well, I didn't really know like their backgrounds and what they thought about it, first of all, so I didn't really have a good starting point on what their biases were and their backgrounds. And what this led to was this sort of kids going home and talking to parents at the dinner table, and kids do what kids do. And I'm sure after a while I had 3 of the students confess, well, yeah, we did exaggerate, and we did kind of make up stories and say some things that we shouldn't have said. And I said, that's really a very costly maneuver on your part. And this is a quote from sort of the leading parent. Peer-reviewed science is the Kool-Aid that the liberal left-wing conspiracy is serving up to the public. And this was where they were coming from. And so what that really unveiled to me was a sense of distrust that some of the general public has of science in general. And so I started realizing that I couldn't just hit them with a concept like climate change it was like hitting somebody with a sock full of rocks. They weren't ready. You know, I have to take it a little slower to make sure that kids are understanding the science piece of it. And I'm not talking about the politics or the solutions part of it. I'm talking about just the basics of climate science. And so I started taking a different approach, which I refer to as integration. And for the last couple of years, I don't teach climate as a standalone unit. I do kind of teach it as a standalone unit, but it's at the very, very end. It's a culminating unit. I take aspects of climate science and sprinkle it throughout my curriculum, and I don't even mention climate change until probably around March of the school year. I just kind of teach about climate science. I talk about how the climate has changed, but I don't talk about climate change. I kind of keep that kind of separate for a while because they're not really ready for it. So integrating the climate science throughout the curriculum. I'm going to give you some examples from the two courses I teach, Earth Science and Environmental Science. And I have taught in the last 2 years. I've taught both honors and regular Earth Science. Our honors course is a weighted grade course, and I use a college level textbook, but it is for, both courses are for 9th graders. Environmental Science, I have both regular and AP. And again, the regular is just sort of a general audience. Some of those kids should be taking it as an AP course, but they don't want to work that hard. And then some of them really could not handle an AP course. So it's my regular environmental class is a group of very, very diverse learners. I also have the Green Team, which is my little club. They go out and they do things like we'll go up to the mountains and dig snow pits, and they learn all about the environment in Colorado. And that's actually my principal. My current principal, who's in the snow pit, he's a level 3 avalanche awareness instructor. I'm pretty lucky to have a guy like that who's climbed Denali, climbed Rainier, climbed Aconcagua as my principal, because he's very, very in tune and very aware of some of these issues. And he's a good guy. And right now, we are, my school, we wrote some grants and we're getting solar panels on our building and a new ventilation system, which is much more efficient. We don't have air conditioning in our building, so because the building is at 7,500 feet, you don't really need air conditioning except for 2 weeks out of the year. And the kids, every year the kids perform energy audits to make sure and to make sure that we're doing what we can and to educate. So that's kind of my integration approach. Now in Earth Science, when I first started teaching, standards had just come out, and I'm like, you mean the government is going to tell me what I have to teach? Well, what do they know about science education? Because I was kind of like my kids I didn't really trust people to do a good job. I knew I could teach well, and I knew that they'd get good stuff, and I knew that they'd learn, but I wasn't sure that other people could actually do it. So this was kind of my perspective. And what I've come to believe is that in many ways, standards are my new best friend. Because even if your local standards don't contain climate change information or expectations, the national standards do. So in Earth Sciences, my standards include some information on Earth chemistry, natural resources, geologic time, plate tectonics, atmospheric sciences, and finally astronomy. And I have integrated climate into all of these, including astronomy. So in Earth chemistry, I talk a little bit about specific heat capacity. And they heat up all sorts of things, and they notice how they cool down, and they play with that. We do get into molecular structure, and starting with this next group, I will be teaching resonance, because I just have recently really understood that. Here's a little interesting aside on that, on the concept of resonance. I live and work with a PhD geochemist. And when I was explaining to him how greenhouse gases work, he's like, no, that's not right. And this was like 3 nights ago. And I'm like, yeah. And so I get on and I'm showing him some stuff that I've found. And he's like, I thought it was all in the upper atmosphere. This is the level of lack of information. And he thought that all the heating of gases, all it did is it made them move faster through space. He didn't understand that it made them move vibrate within their own molecular structure. So it's an interesting fact that we have PhD scientists out there who don't really understand some of these concepts, because it just hasn't been something that has been at a very base level brought into sort of the public awareness. I also teach, of course, about conservation of matter and energy within this unit. So specific heat capacity, they do the lab, okay? This is, the pink line is Dodge City, Kansas. The blue line is San Francisco. And it's remarkably similar to if you take dirt from our backyard and water from our tap and you put a heat lamp on them, turn the heater on for 10 minutes, turn the heater off for 10 minutes, this is the same curves you get. So it's pretty fun to teach that lab and then show them this graph and they're like, whoa, it looks the same. Greenhouse gases, what the molecules look like and how they work. And then the idea that one of the big things that I've encountered was the idea that when you burn a gallon of gasoline, how much CO2 that produces. And the kids are like, well, it can't because of conservation of mass. And I said, oh, but you're only looking at the carbon part of the mass. You're not looking at the oxygen part. And that when they start to look at both pieces going into that, then they start getting a better sense of that conservation of matter. And that, once again, it kind of gets to the idea of, oh, you mean balancing chemical reactions is important? We really should know that stuff. In my natural resources, it's pretty obvious. In this one, it's very easy to do. It was obvious for me that I was going to focus on traditional energy resources, conservation, and making a budget. So I make them make a budget for themselves, a money budget. And they have to sort of figure out, okay, if I am spending more than I make, I'm going to run out of money. And we're burning more than we're making, so we're going to run out of fossil fuels. I bring in the carbon cycle game at this point. So just to get them thinking about where does the carbon come from that's in the ground? Where do fossil fuels come from? So this is where I play the carbon cycle game. And then my solution at the end of this little chunk is to get them thinking about renewable energy resources. And because we're getting solar panels on our building and we already have a little micro windmill, they're going to be doing a lot of work with our in-building pieces, which is kind of fun. If you guys have questions, please interrupt me. I'm good with that. Geologic time. So I had this old diagram that I'm like, you know, I don't really know if I know where the source is, so I had to go and look it up. And this isn't a very good picture, but I'll put this on the wiki, and it's a very technical paper. But what this diagram is showing is how over geologic time, from 600 million years before present to present, what has happened to carbon dioxide. Now kids are going, but carbon dioxide is a lot, there was a lot more way back when. I'm like, that's right. There was a lot, you know, 550 million years ago, because photosynthesis was only starting to kick in. And so here's that piece of being really transparent in the science. Making sure that kids understand that carbon dioxide has existed in the atmosphere at much higher concentrations than it does right now. Makes them think, oh, so she's not one of those carbon dioxide is increasing people. No, I'm just telling you the truth. I'm telling you the facts. This is the data right here. So when we look back in time, you can see where land plants evolved. Can anybody figure out about where land plants evolved? Well, ocean plants around 400 million years ago, and then we got that real nice flattening, and then there was an extinction about 250 million years ago. And then you can sort of see that carbon dioxide continuing to drop to present day levels. Okay, so do you guys understand how I use this? It's a real clarifying point on the science. And it's that transparency piece that is so critical. The other thing I teach about is that they kind of do this comparison. Okay, where does oxygen increase in the atmosphere? At what points in time does oxygen increase? And at what points does carbon dioxide decrease? And what they start to realize is that they are at the same time. So carbon dioxide is decreasing stepwise where oxygen is increasing. So it gets them thinking about the carbon cycle and what's happening with oxygenating the atmosphere and all that stuff. So this is a really, really important piece of what I do in my earth science class. In plate tectonics, they start thinking of, one of the data pieces for plate tectonics is the fossil data. So either the climate was different, or the continents were in a different place, or both. And so kind of bringing that up again, bringing that to the surface and getting kids to think about how where things are on the planet changes what can live there. So that's that kind of linking it into the biology and ecology piece. And then also during plate tectonics, I introduced the idea that when volcanoes erupt, they put gases into the atmosphere, and this is where the original gases in the atmosphere came from. And so these gases had to be changed by something, life, to develop the atmosphere that we have today. Okay, am I going too fast? Are you guys good? Okay. Okay, then finally in atmospheric sciences, we go through and do a very detailed structure, history, and composition of the atmosphere. I get into climate fundamentals, what I refer to as forcings and feedbacks. What are the things that make climate the way it is in any one place on the planet? Yeah. So what I'm trying to show you is how I take pieces of it and I put it through my whole year. History of climate, so I do a very explicit thing on the history of climate and go back to those data sets that I was using before, ice core data, tree ring data, and so finally getting into a little bit and talking about scales of time. So I talk about how when we look at different time scales, we see different things, and that's an important thing for the students to understand. We see time, really pretty much humans do, on years to tens of years. Rocks see time in millions to hundreds of millions of years. Okay, what does ice see time as? And so you can get into some of that. And then finally we do get into some predictions of future climates. And how I do this is I use the IPCC report, Summary for Policymakers. And in that report there is a piece where if you are a farmer living in Indonesia, this is some of the changes that you might expect. So what I do is I take all my students, and each table group would be a different part of the world. And each person at the table is going to have a different occupation. And then they go and they do research using the IPCC reports and other online resources, and they find out how could a changing climate affect a farmer in Indonesia, or a water manager in India, or Russia, or a forestry person in Siberia. So they look around the world at these different occupations and they try to understand that. Here's a diagram, and I will try to figure out where I found this. I'm pretty sure, I generally only use things where I know the source is good, but I'll go find this again. But this is a diagram showing this idea of feedbacks and forcings. And the blue arrows, which are most of them, are positive feedbacks. So talking a little bit about positive feedbacks, I take food off my brother's plate. He takes food off of my plate. I hit my brother. He hits me. We end up on the floor wrestling. That's a positive feedback. Okay? In other words, it's just getting bigger and bigger and bigger and bigger. A negative feedback is I give my brother my dessert. And he loves me. And that's a negative feedback. So I try to really take feedbacks and turn it into something that they're going to understand. And so this just kind of goes through a lot of the stuff that we've been hearing about. Decreasing sea ice, more absorption, warmer planet, blah, blah, blah. Okay. In astronomy, I do a little thing on the Goldilocks effect, comparing Earth to Venus and Mars. Mars is too cold, Venus is too hot, Earth is just right. And just I spend some time just comparing the planets and talking about why, how they're different and why they're different. And actually getting into the atmospheric, what we know about the atmospheres of Venus and Mars is really a fun process to do, because it makes it very clear that if you have too much CO2, you're going to end up like Venus. And if you don't have enough, you're going to end up like Mars. Well, Mars has enough. They just don't have anything else. Okay, in my environment, so that's it for the earth science. Any questions about the earth science class? Okay, so in my environmental science class, by the way, this is a mountain in Colorado. It's called Vespa Ridge, and it's a huge climbing destination in the San Juans. My environmental science class is divided into 2 semesters. The first semester is understanding natural systems, and the second semester is how we're screwing them up. So semester 1 is all, candy and roses, and semester 2 can get a little depressing, so I actually do bring in candy to try to make them feel a little better. So we talk a lot about the biosphere, the cycles, the ecosystems, limiting factors. This is where I introduced the pine beetle project that Melissa and I worked on last summer. We do work on biomes, and I'll get into, well, I'll talk a little bit, well, that's second semester. But so these are, I just kind of give an overview on the biosphere and ecology and ecosystems. The same sorts of things that you've been teaching all along if you teach ecosystems. Oh, and succession. Succession is an important piece of this. So I spend a few weeks on that, and then we spend some time on the water cycle. So, you know, first semester is just really rolling along, and it's reviewing a lot of stuff that the kids have already had in earth science and biology. They are required to take both those courses in our school, so in our district. So by the time they get to me, you know, they have a good background. Atmospheric history, composition, and structure. I get a little bit more detailed. So they'd already seen some of the data in earth science. So this is a little bit more detailed in terms of history, the CO2 temperature relations with time, and gets into some of the ideas of time scale and data sets and where do we get our data and how reliable is that data. The green band around in the top graph there are the error bars. So you can talk a little bit about error bars and what that means, and you know, geologic data is difficult. The further you get back in time, the poorer resolved it is, and so that can be challenging. Composition, of course, and I always break out that tiny little skinny wedge of trace gases and show them what it's made out of. So in environmental science, we get into more details about this. And then, of course, the structure piece. And I really try to differentiate between tropospheric warming and stratospheric ozone issues, so that they have a really good handle on those two, the differences between those two things that can get so easily confused. Students so often confuse the ozone hole with global warming. And if you spend time on the structure and talking about the structure of the atmosphere, you can avoid a lot of that. And then finally, the geosphere. This is actually a NOAA diagram showing the age of the Atlantic basin. So we review geologic time, the rock cycle, plate tectonics, distribution of rocks on Earth. And the primary reason I do distribution of rocks on Earth is because when we talk about oil resources in environmental, it's really important for students to understand that not everybody has the same amount of oil. So there are certain countries that have a whole lot of oil and other countries that have none at all. And so if they understand that the distribution of rocks on the planet is not even, and that some places have and some places don't have, then they're going to understand the politics of some of these issues a lot better. And in AP, you have to get into some of the politics because it's part of the required content. Second semester is, this is sort of where kids are when we start second semester. So population is probably the most difficult thing I teach because it can be so depressing. We get into the actual number of people on Earth, but more importantly, allocation and distribution of resources. Who is using what and how much are they using? And when they realize how much they're using compared to a person of their same age in Africa, they're like, I suck. You know, I'm a greedy, you know, little monster and I don't deserve to live. Yeah. When we get into resources, so now, you know, you go from allocation and distribution of resources to what resources are we talking about? Well, primarily energy and fossil fuel, revisiting the carbon cycle, and then once again I hit renewable energy. And in this particular class, what I do is I spend time on the issue of renewable energy as a way to become, to basically gain more national security. It's a huge, huge thing. If we didn't rely on the oil of other countries, we wouldn't have as many national security issues that we do. The fact that fossil fuels are limited, we don't have an endless supply, and that when we burn them, they pollute the atmosphere. So those are things that renewable energy is always a solution. So you can bring those in. Besides just climate change, you can bring in renewable energy as a solution to these other issues. Okay? And then agriculture, distribution of food resources around the world. And I do get into diet modification and GMOs as a solution. And with GMOs, you know, they're creating seed crops that can handle much more stressful conditions. And you have to decide, you have to figure out if you want to include that in your course or not. But I spend time on that because people are starving. and food is not distributed evenly around the world, and are there ways for us to get around that? But then there's the issues of Monsanto owning all the rights to all the soy in the world. I also tell them at this point, if you want to be a millionaire, get into energy resources. Start investing, go to college, get a degree, and start, become a chemical engineer or an environmental engineer. You can earn a very nice income and have nice job security if you get into these issues of energy and agricultural stability. Yeah. There was some mention of this earlier. This is the two maps at the bottom are the hardiness zone maps from 1990 and from 2006. And the map above shows the anomaly. So how have things changed from 1990 to 2006 in 16 years? If it's red, it's warmer. If it's yellow, there is no change. And if it's blue, it's cooler. So this is the Arbor Day Foundation's hardiness zone map for agriculturalists and gardeners, so that people know. We can now raise figs in Colorado, okay, down by Grand Junction. That has never happened up until the last 10 years or so. But these maps are really, really great to show biodiversity and the effects of humans. Like if we just talk about climate change and warming, what are some of the effects? Well, the rate of change has been very rapid. So in 16 years, you can see how much of the map has warmed versus cooled. And this is hardiness zone, so the lowest freezing temperature. And then we talk a little bit about mobility of species. Well, I'm fine. I can get up and go wherever I want. We can grow different food crops. What about maple trees in New England? They're really worried about that. What about bristlecone pine in California? They are creeping, they can't like walk up the mountain to get into cooler areas. What about picas? What about some of these other species that we've heard about? They can't just up and move. They don't either have the lifespan or the legs to do so. And so what that will lead to is extinctions. So you either move or you die. Yeah. And then we get into pollution and climate change. Now I'm talking about climate change. At this point I introduce the idea and I get students' perspective on climate change, and I want to find out, what do you know, what have you heard, what do you think? Tell me where are you at this point? What's your background and your bias? And I introduce a problem-based learning module that is put out by the Earth System Science Education Alliance. And this group has a set of lots and lots of different modules that are problem-based learning. The nice thing about problem-based learning is it's very student-directed. And so in general, I mix up how students are grouped. And in this case, I choose their groups because I want them to be working with diverse groups of thinking. So based on their early, the unit survey, the pretest, which is basically, what do you know, what do you think, what's your background, I take those and I mix the kids up so that they're working with a group of diverse thinkers. So that it's no longer just, well, all of the people who go to my church and think the way I do are going to work together. Because that was what happened 2 years ago, is I let them choose their own groups. And they decided that they were going to overthrow me. They were going to mutiny. Biggest thing I can comment here is stay focused on the data. Use my NASA data resources. They have some lesson plans in there that are really good. Some of them are not so good, but most of their lesson plans are pretty good. If you're a GLOBE teacher or you're interested in GLOBE, get involved in GLOBE. Use the data that they have on their website. NOAA Paleo Climate Data is also a great resource, and there are so many other resources, and we've put a bunch of them on the website, so please take advantage of those. I do talk about models and climate models, mitigation, adaptations, and solutions, and go back to the IPCC report policy. I don't do the same jigsaw that I do with the younger kids, but I do have them go through that, and it's a homework assignment that they have to write a short paper on. This is just a picture I'm throwing in from the IPCC report, and what this diagram is showing is the pink, or I'll start with the blue. The blue bands on the graphs, each graph is for a different part of the world. The blue shows what the models say would happen if there was no anthropogenic warming. The pink shows the models with anthropogenic warming. And the black line is the actual data. Okay? This is the IPCC report, policy report for summary report for policy makers is what it's called. So this is a pretty nice diagram, and kids they understand it at 11th and 12th grade. They can understand this. So who are we doing this for? This is our mindset. We're doing this for our kids. We're doing this so that and those are my kids, aren't they cute? We're doing this because we want to make sure that they have a good place to live. So it's important to stay as objective as possible. You have to remove them from the picture to kind of keep that objectivity. It's so important to develop and share high quality resources. The more we have more brains working on this at our level, the better our teaching is going to be. Networking with each other and with local scientists, business owners, if you have business owners in your communities who work in green business, get them involved. Communicating, being proactive. So I've already sent an email to my principal and my superintendent asking them for a meeting in August so that we could sit down and talk about what's happened in Mesa County and how that's going to affect teachers, both earth science and environmental science teachers in our district in Jefferson County in terms of teaching climate change. Because I really want her to be aware of this, and I want her to be aware that there are people in my situation who are thinking about this. Talk to them, though. I think people will hear us. And rely on the standards. Every time you get together with one of these people, talk about the standards. If your district standards or your state standards don't have climate change written into them, go to AAAS, go to the National, and what is it? National Resource Council? I can't remember. The science education standards. But go to those because they all have climate issue standards in them. But I think one of the most important things is to stay positive. I would not have given birth to 2 children if I thought that the world was going down the drain. And I tell my students that. And so I think staying positive is really important and offering solutions.